Okay, as we discussed, today we are going to learn simple harmonic motion. So this is a big lesson which carries 150 marks in your applied mathematics paper. In this video we have, in this session we have 2021 and 22 both badges. So I'm going to start from the beginning. First we'll discuss what are the important equations that you should know to solve simple harmonic motion problem. First one is the characteristic equation of a simple harmonic motion. That is x double dot equals minus omega square into x. X double dot means the acceleration. Omega is angular velocity. This is acceleration. This is angular velocity. So these terms you have learned under physics. X is displacement. Then let's consider we have a particle of mass m which is connected to a string like this. This is the string. This is a slacked string connected to a mass m. So when we stretch the string, let's say it can extend up to a distance like this. So this is an elastic string. That is the importance. In physics, under mechanics, you have learned about inelastic strings. They can't stretch. But in simple harmonic motion, we deal with elastic strings. They can stretch to a certain extent. Therefore, they have a special quality, a special constant that is called modulus of elasticity, normally denoted by lambda. Elastic strings have a constant called modulus of elasticity. Then, according to that constant, these elastic strings can extend. But here, I have taken this mass m to a distance which is the natural length of the string. Natural length of the string is n. If I am going to further stretch, then this separation will increase beyond the natural length of the string. This part is the extension. Let's label that as x. Extension of the string more than its natural length. So when we do this, there will be a resistive force which opposes my movement. This resistive force in the case of a string is called tension. That tension is always equivalent to m omega square x. This resistive force, tension, is equivalent to m omega square x. So m is the mass of the particle, x is the extension, omega is angular velocity, which will be given in the problem. This thing we should know. Then for our problem, we have to apply Newton's second law of motion, F equals ma, to this direction. The reason I choose right hand side is I am going to measure the displacement to that side, right hand side. So we have to select the same direction. X measure කරන්නේ right hand side එකට හින්දා F equals m එකේ direction එකත් ඒකම. Then when we apply forces, this T is opposite in direction. So it is minus T. M, what is the acceleration? That is x double dot. So if you have done this differentiation, you know if displacement is x, when I differentiate displacement with respect to t, I get velocity. That means velocity is the first derivative of displacement. When we differentiate displacement by time once, we get velocity, that is denoted by x dot. Then when we differentiate x dot, which is velocity, with respect to time once again, then we get acceleration. Velocity divided by time is acceleration. That is second derivative of displacement, that is denoted by x double dot. So in simple harmonic motion, we substitute x double dot for acceleration. So what is t? That is m omega square x, negative because of the direction. Here we have mx double dot. Both side masses get cancelled. Then we have our characteristic equation, x double dot is minus omega square into x. Therefore, acceleration is dependent on the displacement of the particle under motion. This is a constant. Omega square is a constant which is to be determined. That depends on the problem. This part is very important. For every simple harmonic motion problem, you have to apply this. First, you should mark the forces and apply F equals ma. Then, you have to arrange your equation according to this. This is the form that you have to get. X double dot equal some constant into x, displacement. But in some advanced problems, you will have that x part like this as a bracket. That is the difference. Here you may have x minus a, x minus 2a, x minus a by 2. Likewise, you can have some brackets without having just x. Okay, so this is the first derivation. This is the most important equation in simple harmonic motion. Then the second one, you should know how to find the velocity. Velocity square is equivalent to angular velocity square times amplitude square minus displacement square. Every term in this particular equation is squared. So you should know the terms. This is velocity. The important thing is this v represent the velocity of the particle at the point we are considering. Let's say we have a simple harmonic motion. At this location, we know the velocity of the particle as v. Then this is the center of the simple harmonic motion. This is the center. Let's say we have a displacement to this particular point, x. Then now I'm going to apply this equation to point A, capital A. Then with respect to point A, this equation is like this. Here the velocity is v. Omega square is a constant for entire motion. Then amplitude is also a constant. Let's say it is capital A minus. Then what is this x? We have to measure x from the center of simple harmonic motion. Then we have to measure the distance to the point that we are going to apply this equation from center of motion. Center of motion is here. I am going to apply this equation to the same point. Then is there any distance between point A and center? No. Therefore, displacement is 0. X is 0 here. Let's consider this point as B. Now I am going to apply this equation at B. Then here the velocity is u, for example. Then u square is equivalent to omega square, that is a constant for entire motion. Amplitude, that is also a constant. Then the only difference is x. Now we have to measure the distance from our center of motion to the point we are applying the equation. Now the displacement is given as x. Here we have to put x square. So this is the difference. That is the distance from the center of motion to the point that I have taken the velocity. Here I took the velocity as v. Displacement is, distance is 0. Here the velocity is u. Distance from center to this particular point where the velocity u is x. Therefore I have to put x. This is the second equation. Third equation is regarding time. In simple harmonic motion, you have to measure time. Under physics, you have this t, capital T equals 2 pi over omega. Period of motion is equivalent to 2 pi over omega. So in applied maths, we have to calculate time of motion. That is equivalent to angle covered by simple harmonic motion divided by omega. So we should know this. To find time, we have to divide covered angle divided by omega. Then the method used to measure the angle will be discussed using a question. Then fourth equation is tension of an elastic string. How to find the tension of an elastic string? Let's say we have a string, elastic string of natural length L. It is freely hanging vertically down. Now I have connected a mass M to that elastic string. Then definitely it's going to extend downwards. Let's say that extension is simple E. Natural length is L. Then we can, before that, there is the tension T upwards. If the mass is in equilibrium, we know tension is equivalent to mg. And also, there is another equation for tension. If we know the constant modulus of elasticity, that is, tension is equivalent to modulus of elasticity into extension over natural length. Modulus of elasticity into extension over natural length. This is the equation for tension of an elastic string. Then, if we have a spring, this is the last one. If we have a spring, So this is a spring of natural length A. When I place the mass mg, what will happen to the spring? It is going to compress. This is a compression. Let's say the compression is simple C. Then there is that weight of the mass mg and opposing force created by the spring. Now it is going to expand. That is a kind of a tension, but that is for a spring. For springs, you know from your physics knowledge, there is a constant called spring constant. Okay, this law taught in physics is Hooke's law. Then tension or the force, opposing force created by a spring is equivalent to the product of spring constant into C. This is C. Spring constant into C, Kc. So these are the 5 equations you should know in order to simplify simple harmonic motion problem. We have our characteristic equation, velocity equation, time equation. I think you have not much of an idea about this angle thing. Don't worry, I will explain that using an example problem. Then tension of a string, tension created by a spring.